Hello, welcome to Electronics Education. I am Vincent Chang. Today we are going to continue our lesson on the MOSFET small signal model. But actually we are going to close this series and move on to the bipolar small signal model after this lecture. But the final lecture now, we are here now, is to apply especially what we learned from the previous lecture, which is the MOSFET internal capacitances and high frequency model, and going to find out what is the high frequency response of the MOSFET's current gain. So this can be this could be placed in the frequency response courses instead of the semiconductor devices. But I think if you have a little bit background on the frequency response, then you can understand this lecture. So MOSFET Unity-Gain Frequency, I will define this term later, but basically it's to find out the device, the high frequency performance, especially for the MOSFET's current gain. So let's start with the MOSFET Simplified high frequency model, which is what we learned from the previous lecture. And then under certain condition, the phi internal capacitances can be reduced to the two capacitances we are seeing right now, where the CGS represent the gate to source capacitance and the gate to drain CGD. If you are struggling in accepting this model, then you have to go back to the previous lecture. But anyway, this is the simplified high frequency model. So now, H parameter model, okay? So let me just give you a quick lesson on around this H parameter model, but in the bipolar small signal model you are gonna learn in the future, I will develop the whole lecture around this H parameter model. Make sure you have the full comprehensive understanding around this. But anyway, let's just let me just quickly show you what the H parameter model is about. Basically, there are four parameters. H11 is the two-port network. H11, 12, H21, and then H22. All right? And the meaning of these four parameters is the input resistance, reverse voltage gain for H12, and forward current gain, and output conductance. I know maybe this slide will cause you a lot of headache already, but just bear with me for a moment. Just accept the definition for so-called forward current gain. Again, I will develop a full lecture around this so in the future, so no worry. So just focus on the highlight on your left-hand side, which says the H21 is the I2 over I1. So look at the model. So I2 is the output current, right? And then I1 is the input current. So output current divided by input current, then it's supposed to be a current gain. But under what condition? Under the output, the V2 is now short circuit. So V2 is 0. So let's just accept this definition for the so-called the forward current gain. And then try to apply this definition and find out this current gain's performance in the frequency domain. So now, apply the definition from the H parameter model, then, because the definition is V2 has to be 0. The VDS on your right hand side. So you see, the VDS now, before is this, and then after we apply the definition, now the VDS is short circuit. And we send in, on your left hand side, you see a gate current. We send in an input current. And then the output current is taken from the ID, corresponds to the I2 earlier in the H parameter model. So based on this definition, then we can write down this. So I2 corresponds to ID, and IG corresponds to the I1. VDS equals 0 corresponds to the V2 equals 0. And F, the first subscript, represents the forward current gain. And the second subscript represent the common source configuration. So under the common source configuration, so it's the common source short circuit. Who got short circuit? The output terminal. So it's the common source short circuit current gain. So HFS represent the common source short circuit current gain. All right. So we're gonna find out this. This is not a constant because this is in the frequency domain. A complex frequency domain because the two capacitance now are involved. So then let's focus on the ID. So ID, because the VDS equals 0, then the current going through RO equals 0. And then high frequency, look at the title, analysis. So then you got to consider this. You see the purple current? So the purple current, the voltage across the CGD is what? So pay attention, the output is now short circuit. So the voltage across the CGS now is the same as the one across the CGD. So the CGD, the GD's voltage is also VGS divided by the impedance. The impedance is 1 over S CGD. So then it turns to the S CGD VGS is now the purple current. Then we apply the Kirchhoff current law, the node equation at the drain. Then what do you have? What would you have? So the two current, the sum of two current equals GM VGS, right? So then the ID will equal to what? GM VGS minus S CGD VGS based on the Kirchhoff current law. So now, let's make an assumption. Suppose the transconductance is much greater than omega CGD. Usually this requirement will be met. It's reasonable, especially if you study more around the frequency response, high frequency response of all kinds of amplifier. So most of the time, this condition, this assumption is a very good assumption. But I don't want to, since this is not a class for the courses for the addressing, focus on the frequency response of the amplifier. So then I'm gonna just move forward, okay? So this is an assumption. So under this assumption, the second term is negligible. So then you can just focus on the first term. In other words, under this assumption, the AC current, the high frequency current going through the CGD is now negligible. So we assume the high frequency drain current, the high frequency output current is solely contributed from the voltage control current source, the GM VGS. All right. So now let's focus on the VGS. So VGS now equals what? Equals the input current. The input current. Input current is the IG. The current going into the gate, the flowing into the gate, times the impedance between gate and the ground. So the impedance between gate and the ground, not just the CGS but also the gate to drain needs to be considered. So it's the parallel combination between the two capacitances, all right? So I, the current, times the impedance. So impedance is 1 over S capacitance. And the parallel capacitance is just the addition, the sum of the individual two. All right? So then you got this, the left-hand side of your slide. The output current divided by the input current. So this is the outcome. So this is the result. This is the high frequency transfer function, the current transfer function. The high frequency transfer function of the MOSFET. So its magnitude response of this current gain, magnitude response of this current gain is going to go like this, right? And the high frequency slope is going to be the negative 20 decibel per decade of frequency. If you stuck on this, cannot follow this, then I suggest you just pause and think about this. You see what changed? The straight line is not changed, but the current gain becomes the voltage gain, right? So which circuit associated with this? Associated with this frequency response, the integrator. If you have ever learned the fundamental microelectronics, the fundamental microelectronics circuit, especially around the op-amp, focus on the operational amplifier circuit. So you are supposed to learn this before, right? So this is op-amp and RC, an inverting configuration. So closed loop transfer function, look at your right. The closed loop transfer function is negative, and then what? The Z2 on the top divided by Z1, which is now a resistor like this. So then the magnitude of the transfer function, pay attention to the absolute sign. So on your left-hand side is a complex transfer function, represented by the complex frequency S. But on your right-hand side, it's the real number. It's the real magnitude of the complex transfer function. So see the negative 20 log omega. So in the frequency domain, it's going to be a straight line with a slope of negative 20 decibel per decade of frequency. So when omega equals omega 0, 0 decibel. So it's the unit gain frequency for the integrator. And now it becomes what you see changed? Let's go back. This is the integrator. This is the MOSFET. You see? So omega t now is the unit gain frequency for MOSFET device. For the device. The previous is for the op-amp integrator, Miller integrator. And this one is for the MOSFET itself, for a device. And omega t now is what? It's the transconductance of the MOSFET divided by the CGS plus CGD. If you plug in the omega t into this to replace the complex frequency S, you will find out that this frequency is 1. It's unity, 0 decibel. So on your left-hand side, the omega represents the angular frequency. So the dimension of the angular is the radian per second. But this is the frequency, ft, divided by 2 pi. So omega t divided by 2 pi is now in the dimension of the ft is now hertz. So this is the unity-gain MOSFET unity-gain frequency. So here's the takeaway. So takeaway of this lecture is this: the frequency response of the common source short circuit current gain of the MOSFET. And pay attention to a very important parameter called unit gain frequency. Because below this frequency is an amplifier, right? Above the 0 decibel. But beyond this frequency is the limit. Why is the limit? Because it's below 0 decibel. It becomes the negative decibel. What's the meaning of the negative decibel? Loss. So below this frequency is the amplifier. But above this frequency is the loss. It's a loss. All right? But because this is the course for the semiconductor device physics, right? So if you have some foundation around this, now you know, not just know this. Geometry, mobility, gate oxide capacitance, right? Bias current. But you also know this. So you can understand if someone asks you, if we increase the bias, how this will impact its frequency limit, Ft, then you know how to answer. Also, if we shorten the channel length, geometry, Ft will goes up for sure, right? So we understand the dependence of Ft on the frequency limit on the bias condition and also the geometry and the other device parameter. So this is the major takeaway of this lecture. This is also the end of our MOSFET small signal model. In the next lecture, we're going to focus on another device, bipolar junction transistor small signal model. So see you there. Thanks for watching.